So, welcome to today's lesson in dynamical systems. So, today we're trying to solve some questions, and we have the question here. So, it says that given that this equation here and that equation here, so we can see that this equation here is a second order ordinary differential equation, and that here is also a second order ordinary differential equation. So the two of them coming together gives us a system of second order ordinary differential equations. So the first part of the question says that if capital K is equal to small k over m, we are to convert the above system of second order ODEs into a system of first order ODEs. And the second part of the question says we are to determine the stability of the fixed point at the origin. So we try to go through the solution. So recall that we have, with the A part, we have this equation here and we have that equation here. So equation 1 here and equation 2 here can be seen from the question. So the next thing we do is that we try to take equation 1 and 2, both of them, and divide through by m, this m here, right? So when you divide equation 1 by m, it is going to take the m which was attached to this side away. This one too will go away. And you're going to have q over m here. But note that in the question we said capital K is equal to small k over m. So that means that in place of this small q over m here, we have capital K, right? So that means equation 1 has now been written in this form, has been reduced in this form. Then we go to the second equation. So we now want to divide through by m. So dividing through by m, we are going to have what we have here. The m here goes away, that here goes away, and this place will be k over m. But note that in the question, capital K is equal to small k over m. Alright, so that means making that substitution, we have this to be our new equation 2. So now we have new equation 1 and new equation 2, which can be written in this form. I hope you can see that. So the next thing for us to do is to reduce this system of second order ordinary differential equations into a system of first order ordinary differential equations. So to do that, we have to let certain things be something. So we let x1 to be equal to, we let s to be equal to s1. Then as a result of that, the x dt will be equal to x2. And we end at the s dt because it's a second order ordinary differential equation. So when we are letting, we let it at the n minus 1 order. Then we let y, because we have x here and we have y here. So we let y be equal to x3. As a result, the y dt will be equal to s4. So you could see we have these 4 equations here, right? So the next thing we do is that, so here, know that here we just let it. So someone could have let x be anything. So we are just letting x to be equal to x1, the sdt to be s2, and so on. So now what we do is that we differentiate both sides of equation 1, 2, 3, and 4. So this is equation 1, this is 2, 3, and 4. So we differentiate both sides. So for instance, when it comes to equation 1, we get d dt x, which will be equal to d dt x1. So that is what we are going to do to all these 4 equations. So doing that, we are going to end up with these new 4 equations here. So you can see now this is the new equation 1, this is the new equation 2, new equation 3, a new equation 4, and these equations were obtained by differentiating both sides of what we had above there. Alright, thank you. I hope you understand. So the next thing we do is that, you see we have the x1 over the t is equal to the s dt, but I want to get all our derivatives in terms of x1, x2, x3, x4. We have to find other things to represent. When it comes here, we have to find other things to represent this, here to represent this, here to represent this, and here to represent this. So when it comes to the x1 dt is equal to the s dt, but note that here the s dt is equal to x2. So that means that our first equation will be the x1 dt will be equal to x2, because here the x1 over dt was equal to the s dt, and this ds dt is x2. So that means we have this to be our first equation, so equation A. And when it comes to the second one, we have the x2 dt equals the squared x dt squared. So now this is equal to this, so we have to find for this here, and you realize that this is the squared x over the t squared. So that means you have to make this the subject. So when you make this the subject, then the other things remaining will equate the x2 the t2. So when you make the s squared the t squared the subject, we are going to get whatever we have here, capital K times y minus x minus omega naught x. So but we should note that from the lesson I will let y to be equal to x3 and x to be x1. So making that substitution, we are going to get the x2 dt will be equal to k. So instead of y, now we have x3. Instead of x, we have x1. So this becomes equation 2. Then equation 3, we had the x3 dt equals, let me come up for you to see. So equals dy dt. But note that dy dt here is equal to x4. So that's the reason why in equation C, we have the x3 dt equals x4. And in the last equation, let's name it equation D. So realize that the x4 dt is equal to the squared y dt squared. And when you make that a subject, you are going to get this here. But x equal to x1 and y equals x3. So making that substitution, we end up with this equation here. So now we have been able to reduce the two system of second order ordinary differential equations to a system of four first order ODEs. So these are the four first order ODEs that we had. So we know this is the first one, so equation 1. This is the second one. This is the third one, and this is the fourth one. Alright, so thank you very much. So in our next video, we will try to discuss the stability at the origin of the fixed point at the origin. Okay, so thank you very much for following.